Alrighty then. So, final video for the week, proving shapes. Right now, if you look at these three shapes that we've got right here, I'm pretty sure that everyone could tell me what they are. You could look at it and go, oh, that's a, and that's a, and that's a, and you'd probably be right, okay? If we were looking to identify shapes, we'd be done, okay? But what we're looking to do in this particular section in this course in math is we're looking to prove that the shapes are actually what they are. Okay, so identifying is just like going through the line out. You pick out the guy that does it. Anybody can go through and identify. We know that you've been able to do that since third grade, but we want to actually prove. We want to be the lawyers. We want to be the ones that talk to the judge and convince the judge that indeed this shape is a triangle, this shape is a rectangle, and this one is a trapezoid. Okay, so we need to get to proving shapes. We have the skills to do it. We just really have to put in the time to get it done. Okay, a couple things we need to remember. Both of these should be from Math 1. There's the first one is our quadrilateral hierarchy. Okay, see if you can dig that sheet out from Math 1 where we talk about how they're related. Okay, we've got ourselves the quadrilateral up top. This is my trapezoid over here. Here is a specific type of trapezoid, an isosceles trapezoid. I'm writing sloppily, but I know you have this someplace. We've got the parallelogram. We've got the rhombus, we've got the rectangle, we've got the square right here, and over here, clearly enough, that's a kite. So the idea is that the square shares all the properties of everything up above it. It's a four-sided figure, opposite sides are parallel, it's got right angles, and all the sides are the same. Okay, so what we need to do is we're going to look at proving shapes are one of these based on the properties that we have. We're also going to look at triangles and different types of triangles. So, you know, we know what an acute triangle is, we know what a right triangle is, we know what an obtuse triangle is, and we probably know what an isosceles triangle is, a scalene triangle, and an equilateral triangle. And we know that we can have combinations of, you know, one from column A and one from column B to make an acute isosceles triangle and a right scalene triangle, and we can have other combinations with the obtuse. Okay, some we can't have. So we're going to try to be really specific when we're proving about triangles. Is what exact type of triangle is it? Is it a right isosceles? Is it a right scalene? And so forth. Okay, we're in coordinate geometry, so we're going to use coordinates to get our work done. So the basic idea is we're going to be given some points, and we're going to probably just start out by doing a quick little sketch. -9, 0 is right there. -4, 7 is about there, and 3, 2 appears to be about there. All right, so clearly we have 3 points, so we must be talking about a triangle, right? So we'll connect to those points in some sort of an order, and we can see that we have a triangle. Probably should label our sides. That's Z, that's A, and that's C. And any connection to people, real or imagined, is totally coincidental. So the way we're going to go about this is we're going to use the distance formula, and we're going to use slopes to be able to determine what kind of triangle it is. You might be able to tell by looking, but again, that's just identifying we want to prove. So when we're proving the type of triangle, first we're going to use our distance formula to find the lengths of the sides. So we'll start by finding the length of ZA, and I'm going to go relatively quickly because we've done the distance formula. So it's going to be -9 subtract -4 squared plus 0 minus 7 squared for ZA. -9 minus -4 is -5. So we have -5 squared and 7 squared. -7 squared should say, right? So this side length turns out to be the square root of 25 plus 49, which is 45, 65. I'll get it eventually. 65. How about 74? Square root of 74. Okay. So this side right here is the square root of 74. This side then we'll go and we'll do AC with the same manner of speaking. -4 subtract 3 squared plus 7 minus 2 squared. This is -7 squared. That's 5 squared. And that's going to turn out to be, again, the square root of 25 plus 49, which is 74, square root of 74. So we know at this point these two side lengths are the same. So we've got ourselves at least an isosceles triangle. We'll quickly roll through finding ZC just to be certain that it's not an equilateral triangle. It doesn't look like it is one, but we never want to go by what it appears to be. So when we do this one, on the one side we're going to get 2 squared. That's, I did the y's first, but you'll forgive me. And on this side we're going to end up with negative 9 minus 3, which is negative 12 squared. So that one's clearly not going to be the same length. That's 4 plus 144, square root of 148. So we know that we don't have an equilateral triangle. Next, we want to check out and see about, is it a right triangle? And it would appear that those two might be perpendicular to each other. So we'll need to do a little slope indication. See if I can't move this entire point so that I can see it as I scroll down a little ways. Save me from having to go back up there. There we go. So let's find the slopes of, we'll just do ZA and AC because we don't need to do more work than we need to. We'll do the slopes now. Slope of ZA, and remember slope y2 minus y1 over x2 minus x1. Okay, that one turns out to be negative 9, no, how about, let's do this correctly, how about 0 minus 7 over negative 9 minus negative 4. That turns out to be negative 7 over negative 5, so we call that 7/5. Okay, then we'll do the slope of AC, same formula, 7 subtract 2, that's my change in y, negative 4 subtract 3, so I end up with 5 over negative 7. What do we know about those two slopes? Those two slopes are opposite reciprocals, so we have ourselves perpendicular lines, and so we know that Zach is the right isosceles triangle. And we have proven that, and no one could conclude we've given the information that we need to get there. Okay? Let's move on to our next victim, Clay. Clay, negative 2 comma 3, right there. 3 comma 2, right there. A is a 10 comma 1, that appears to be about there. And y is at 5 comma negative 4, about there. So what sort of shape are we looking at with this particular figure here? Let's get in some lines so we can see what's going on. Okay. Boom. 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 Okay. Perhaps something like that. And again, hard saying from the picture. So here's C, L, A, and Y. So we're going to do the same thing. We're going to do distances. We're going to do slopes. We're going to just, because we've gotten so good at doing them, we'll be really quick at this. We're going to do the distance of CL. So that's going to be negative 2 minus 3 squared plus negative 3 minus 2 squared. That's going to be negative 5. That's going to be negative 5. So we're going to end up with 5 squared plus 5 squared. And we're going to end up with the square root of 50. We can just leave it that way because if we get this side to be the square root of 50, we can make comparisons pretty easily. All right, let's see what the length of LA is. LA is 3 minus 10 squared plus 2 minus 1 squared, square root of that whole mess. That's negative 7 squared, and that's 1 squared. 7 squared is 49, 1 squared is 1, 49 plus 1, square root of 50. Okay, so we've got two adjacent sides that are congruent to each other. Let's continue on our way and let's get AY. AY is going to be 10 minus 5 squared plus negative 1 minus, or how about just 1 minus negative 4 squared. Both of those turn out to be 5s. 5 squared plus 5 squared, so I know one's negative. So that's going to end up to be another square root of 50. Where are we heading on this one? It seems like we've got three sides the same. We don't want to just ignore CY, so we'll get that one. That's going to be, let's see, negative 3 subtract negative 4. That's my y's I did first, but that's okay. Negative 2, subtract 5. We're squaring them. I know I'm going fast, but I know you're able to follow me because it's just sort of mechanical. CY is that one. Square root, this is very awful. Boom, we go there. This one turns out to be 1. This one turns out to be 7. 1 squared plus 7 squared. We get another 50. Okay, so we've got all four sides appearing to be congruent to each other. Does that tell me anything? It might tell me something. Tells me we probably, if we go back, probably have a rhombus. Oops, where'd it go? Went back too far. Yep, went back. There we go. We have ourselves a rhombus because all the sides are congruent. I want to check the slopes to make sure my rhombus isn't a square, so I know it appears that none of them are. Well, let's just do a quick little verification on at least one of the slopes just to be sure. Let me get those points so I can see them. Bring those all down here. Down here. Let's do the slope of CL and LA to make ourselves working out okay. So the slope of CL is negative 3, subtract 2. That's my change in Y. Negative 2, subtract 3. So this turns out to be negative 5 over, let's see, did I do that right? Negative 3 over 2. Negative 2 minus 3 over negative 5. So my slope there is 1. Does that look like a slope of 1? Well, it does, doesn't it, sort of, okay? And then what's the slope of LA? Slope of LA is going to be 2 minus 1 over 3 minus 10. That's going to be 1 over negative 7. So those aren't going to be perpendicular, right? Not perpendicular. So we don't have a square. If we found, for instance, if we found the slope of AY, we would do 1 minus negative 4 and 10 minus 5. So we end up with 5 over 5, which is 1. These two are the same. And so we know we have parallel lines, and we've got ourselves clay, the rhombus. Okay? And a minute and a half to get this last one in here. Notice the difference here is that our little shape here, our little quadrilateral lexi, is in a matrix form. Okay, sometimes we will do that. It saves a little bit of saves a little space, but basically we've got an x-coordinate and a y-coordinate. So if we look here, we're at negative 2, 2. We're then at negative 3, 6, at 1, 9-ish, and then 6, 8-ish. Okay. Anyone want to guess what that one is? It looks like Lexi's a trapezoid, if I was a guessing man, because that certainly doesn't appear to be congruent sides all the way across. Okay. And so basically all we'd need to do to prove that it was a trapezoid was be to show that these two sides are parallel. Okay, if we were thinking isosceles, we'd probably do the side lengths of this one. Time being of the essence, we're going to just scoot right to this particular piece here. So Lexi, let's see, slope of, oops, I've got to put some coordinates in, LEX, I, is that last one. So let's do the slope of EX. Slope of EX is 9 minus 6. 1 minus negative 3. Okay, that's the slope of EX. And so we end up with 3 over 4. Okay, and then we'll do the slope of LI. And the slope of LI is, let's see, 8 minus 2. Okay, over 6 minus negative 2, which gives me 6/8, which is the same as 3/4, which means that Lexi is indeed a trapezoid. Okay, there's something you've never heard anyone say before, that Lexi's a trapezoid, but you heard it here first. That's it. We're proving things. We don't want to identify. We want to actually get to a place where we're proving things to be the way we want them to be. By the way, if you want to earn some bonus points, tell me what's true about the diagonals of this rhombus. Take a look at the diagonal LY and CA. We'll do some work with this tomorrow. It's just about getting the work done, doing the due diligence. Thanks for watching. Hope you pick something up. See you tomorrow. Hey, 14 more seconds. Perfect.